fastest way to prove a fundamental domain for SL2Z?
Well, what I was trying to do was define a modular form. And in order to define a modular form, see, I don't like how modular forms are defined in books. They're like, it's a Q series that's like, to me, that's not what's important about it. Like people say a Maass form, grows at most polynomially at infinity. I don't like that. What it is the reason they're saying that is when you solve the differential equation, you get a Whittaker function, you get an exponentially blowing up solution and an exponentially decaying solution, right? The K Bessel, the I Bessel function.
You want to forget about them.
I want to forget about the I Bessel, so I have a multiplicity 1. But then multiplicity 1 is really about being L2. The key condition, the key criterion as far as I'm concerned, and as far as representation theory is concerned, is to get that Hilbert space, L2. So I want to say everything in terms of L2, but of course then it takes longer to, like, the reason the definition is what it is in the book is because you can say it immediately. As opposed to the proper way, which is what I'm trying to do, which is to build up all the technology so you can say it the proper way, and then immediately conclude that there's a much simpler way to see this, but then you wouldn't know why that is the definition. Anyway.
Right.
Okay, so so let's remember what we were doing. We looked at SL2R and its action on the upper half plane. In fact, which we could identify with SL2R modulo the stabilizer of a single point. We took the point I. This we did. We looked at SL2Z with its generators 1, 1, 0, and 0, -1, 0. So, but again, there's lots more matrices in here. There's hyperbolic matrices. We classified the motions, the classification in SL2R of motions are elliptic motions, hyperbolic motions, and parabolic motions. Maybe we didn't say an easy way to see whether a matrix is elliptic, hyperbolic, or parabolic. Parabolic also is unipotent. Let's talk about that for just a second.
You're saying easier than looking at the eigenvalues?
Yes.
Yeah, we said one dominant wheel.
Yes. So let's talk about that for just a second. So if I have a matrix A, B, C, D, and it acts on a point Z, and let's say it fixes that point Z. Okay, so how many fixed points does this? So let's look at possibilities for fixed points of G in G. Big G is SL2R.
Well,
Okay.
you said that I is fixed by rotation.
That's right. So so rotation matrix fixes I, but I want to know now about given G, what does G fix? Okay, so this is AZ plus B over CZ plus D. So I multiply through and I get AZ plus B is equal to CZ squared plus DZ. And so if I move everything to one side, I think I'm getting CZ squared plus D minus AZ minus B is equal to 0. And now let's solve it. So this is a quadratic. Even I know how to solve that. Z is negative. I'll leave it as negative D minus A plus or minus the square root of D minus A squared minus 4B C negative B. So plus 4 BC all over 2A where A is C. So I'm just taking this, I'm just applying the quadratic formula to this.
Okay, yeah. G in this case, yeah, you said was SL2R.
SL2R, yes.
We're in the determinant one.
That's right. Okay. Yeah, that's going to become relevant in just a second. So Z, what determines whether Z is whether there are two real fixed points, a single double real fixed point, or a fixed point in the upper and lower half plane is whether it's discriminant. So the important thing, z is in reals. Well, there's a z plus and a z minus. Z plus and z minus are real and different, or z plus equals z minus and they're both real. That's if the discriminant is 0. If the discriminant is real, the discriminant is 0, or the discriminant is complex. So we have one point here and the other point is in the lower half plane. Does that make sense? Hear what I'm saying here? Yep. So let's work out what that discriminant is. So d minus a squared plus 4bc. That's the discriminant. Okay, so let's multiply this out. I get d squared minus 2ad plus a squared plus 4bc. Now I can write this as d squared plus 2ad plus a squared. So I'm adding 4ad squared for no good reason. So I'll subtract off 4ad. I'm adding 4ad. So hopefully that's just not doing anything. And then plus 4bc. So I'll do that minus bc. So there was a plus 4bc. There's a minus 2ad, which I've written in a funny way. I've grouped this because ad minus bc is 1. And a plus d, so this is a plus d, which is the trace. A plus d is the trace squared minus 4. Okay, so if this is positive, so that's when we have 2 real eigenvalues. If this is positive, so we have 3 possibilities. Greater than 0, that means that the matrix is hyperbolic. Equal to 0. That's right. That's right. So one way to see that it corresponds to the eigenvalues is to imagine that this is the point z1, and that this would be equivalent to z1 in projective. We talked about how this action, this fractional linear action, is the realization of the projective action. So that's one way to see the relationship. So if the trace squared is trace squared minus 4 is 0, then you're in parabolic unipotent world, and the transformation is parabolic. And if it's less than 0, then you're elliptic.
I guess I didn't understand what you said before about viewing it from the half line.
Yeah. So what does it mean to be an eigenvalue? It means that ABCD times some vector CW is lambda ZW. Right? But if we're going to projectivize things, we can think about the action, the fractional linear action, as W is equal to 1. I mean, I get to rescale my eigenvector. So let's say we set this to be Z1. To be an eigenvector, this is going to be some eigenvalue times Z1. And so that's a fixed point. So being an eigenvector in the linear sense, in the linear algebra sense of being an eigenvector, corresponds to being a fixed point in the projective sense, which is the fractional linear action.
I guess you could also just hash it out. But...
Yeah. Think about it for a minute, you'll see.
Yeah.
So the point is, this is equivalent to Z1 itself.
Exactly, right? Like this is projective, it's literally a fixed point.
Right. So that's why it's a fixed point and not not some lambda times Z.
And you're saying that this corresponds.
Yeah, because what is the action? The action is the restriction of the linear action to this component.
So the lambdas you'll get from this are what you're saying.
The lambdas are really eigenvalues. Yeah, but you want to drop the lambda when you're looking at the projective action. I mean, These two things are equivalent as long as the eigenvalue is not zero. But the eigenvalue is not zero because the matrix is not degenerate. You're an SL2R. Determinants. Okay. So far, so good. And so how can you tell if you're parabolic, elliptic, or hyperbolic? Well, it's very simple. How can this be zero? Trace squared minus trace is a real number. Trace squared minus 4 is 0 if trace is plus or minus 2. So we can think about the absolute value of the trace, since the trace isn't well defined on PSL2R, which is what we should really be working with. Because -1 and 1 have the same action.
But on the square,
Yeah, trace squared is well defined, right? So we can say, well, I'm just going to say trace is plus or minus 2. If you're parabolic, if this is bigger than 0, that means trace is bigger than 2 or less than -2. So absolute value of trace, we can say, is bigger than 2. And elliptic is absolute value of trace is less than 2.
So, are there any choices? And it is sort of a silly question, but are there any choices of elliptic that are special enough to call circular? Circle is a special case of ellipse.
They're all circular. They're all circular. Elliptic is just the nomenclature. Elliptic is like elliptic has nothing to do with ellipses as opposed to circles. It's like if you have a quadratic form, if you have a quadratic form x squared plus dy squared, then depending on whether d is positive or negative, you have a hyperbolic or an elliptic quadratic form. If you have a differential operator, two derivatives in x plus d times two derivatives in y. If d is positive, that's an elliptic operator. If it's negative,
then it just comes to literally just visualizing.
Yeah, the terminology, you can think of the level sets, right?
Exactly.
The level sets of this will be an ellipse. But really what I'm thinking about is this a positive definite quadratic form? Does it only take positive values? Or is it an indefinite quadratic form? So it takes values on a hyperbola.
But then
It's level
when
sets.
you write it like this, x squared plus dy squared, that's definitely like ellipses and not circles. For d
Sure.
one.
Sure. Yeah. So that's why it's called, that's where the name comes from. But the name takes on a broader meaning, which is just positive definite or indefinite. Is the trace greater than 2 or less than 2? And after that. Okay. Right. We had this classification. We talked about it in terms of eigenvalues, but now we have an easier way to see this, which is just traces. And we had this subgroup of SL2R, this discrete subgroup of SL2R. Maybe that's the thing that I didn't give complete justification to, but maybe you can sort of imagine why the integer entries of something would be discrete and the real entries of something. And then we found a fundamental domain.
Yes, they quickly see the criteria that we're talking about. Translation in space 2.
Yes,
And the inverted in space 0.
that's right. Exactly. So this immediately you can tell without computing anything. You just add the diagonal entries and yeah. And here, this one's unipotent, this one's elliptic. But of course, when you take words in these things, you get hyperbolic. I mean, the vast majority of the elements of SL2Z are hyperbolic. Sure.
I guess.
Yeah, we can talk about the sense in which that's a true statement. And then we found a fundamental domain for the action of, I don't mean the unit disk, D, for the action of SL2Z on the upper half plane, or PSL2Z. You can do this the right way. On the upper half plane, we saw that it was, again, you can translate to get the real part between -1/2 and 1/2 by translation by 1. And you can invert using our other guy to get outside the unit circle. And so this region here, the open region, is a fundamental domain. Any point can be moved inside the closure, and any 2 points that differ by an element of SL2Z are actually the same. Same definition of fundamental domain. Okay. I still am not ready to tell you about the definition that I prefer of a modular form. Yes. So there is a canonical way. So there's something called a Dirichlet domain. So given any, let me say what this is. So definition, given any point, let's call it Z0 in any space, but let's stick to the setting of the upper half plane. Given any point such that, and you have a discrete group gamma acting on this. So like SL2Z, but it could be, this is a completely general fact, given any point, base point, which is not fixed by an elliptic element of gamma, such that the stabilizer of Z0 in gamma is trivial. I'll explain in a second why you need this condition. There's something called a Dirichlet domain, a Dirichlet domain. In this case,
Then there are.
there are, yes. In fact, if you use I in this definition, then you'll get the wrong answer. That's right. That's right. Well, there are lots of other elliptic points. All the images of I and this thing are all elliptic. So a Dirichlet domain for gamma based at Z0, is the following. It's the set of all Z in the upper half plane, so that for all gamma in gamma, but not the identity element, the distance, now we have to talk about distance, so I'm a little ahead of myself. The distance between Z and any to Z0. So let me draw a picture so you can see what's going on.
Shows us in the hyperbolic sense.
That's right. That's right. So, but in general, there's something just that if you have a metric space, you have a metric space and a discrete action on that metric space. So I have my base point Z0. Okay. I have a point Z. So when is Z in the fundamental domain? So here's my region D sub Z0. When is Z in my fundamental domain? When the distance from Z to Z0 is smaller, Z is closer to Z0 than all orbits of Z. Is less than the distance to. So the distance from Z to Z0 is smaller than the distance from gamma Z to Z0 for all gamma that are not the identity. Well, okay, if I'm taking out the identity, then I can make this a strict inequality. You have a choice of Z0, yeah. So I'm saying for any Z0, there exists a domain like this. So let's test our understanding. First of all, why do I want to make sure that the stabilizer is not empty? So what if we take this set? So here's a test question. What is DI for SL2Z? I want all the points that are closer to I than any orbit of I. Right. If I am not, yeah, okay. So that's one thing. If I don't put an equal sign here, then it's a singleton. If I do put the equal sign here, yeah. So why do you say singleton? Yeah. If I want strict inequality. Well, yes, that's a good point. Yeah, but distance, I can apply gamma to, this is also the distance if you have if your distance function is, if your action is an isometry. Again, I'm getting ahead of myself. I have to say all these things properly. Exactly. This is the same as the distance between Z and gamma inverse Z naught.
And this is including the boundary.
So this would be a closed set, not an open set. So that's one of the issues if you well, this set is just, I'm defining this set DZ0. My claim, I mean, this is just definition. My claim is that this set is in general a fundamental domain for the action. You take this, it's like a Voronoi set. You take all the, you know what a Voronoi decomposition is? This is how you this is how Netflix knows what movies you like. You know, there's like the large high dimensional space of the things that you like and lots of other people, and then it sort of has this Voronoi decomposition of the distance, you know, the things that are closer to you than all the things that are farther from you.
Just make it biology.
Yeah, yeah. So if I have a bunch of points, I can take the bisectors, bless you, between all of them. I can take all these bisectors, right? And here, and now I've decomposed the space. So this, yeah, there you go. There's a Voronoi. There's a nice Voronoi cell, right? So these are the regions that are where you're closer to one point than you are to any of the others. So that's one way to decompose things. Decompose the plane into domains. Yeah. Yeah.
We have the line.
Yeah, so that's what this is mimicking. This is saying at a fixed base point, who's closer to I than anywhere else. So the reason, if I don't put an equal sign here, then as Nick was saying, so here's I. If I take a point Z, well, there's an image of Z, gamma Z, which is just as close to I as Z itself. And so that's true for any Z. And so there are no points that are strictly closer to Z0 than to that. If I allow the equal sign, so fine, I'll allow points on the boundary. Then what domain will I get? Well, certainly I'll get the classical fundamental domain, because these points are closer to I than any of their, or like this point is definitely farther from I than that point. And this is the image of that one under translation, right? Yeah, so certainly the standard fundamental domain is there, but there's other points that are also closer to I than any other images, or as close to I as any of its other images. Exactly, this bottom thing. This bottom. Exactly, it's the action. So what happens if you forgot to check this condition, as has happened to me several times, which is why I'm subtle. I'm sensitive to this condition, is that sometimes I'm trying to draw a domain of something that I don't know what it is. Like I don't know what I'm given a bunch of matrices. Yeah, I have some random matrices that are given to me. So what do? I take a base point, bless you. I start moving it around. And then I say, okay, so here's my domain. I'm close. This is my midline. This is my midline. That's my midline. And that's my midline. This is a nice domain. And then wait a second. No, this point is stabilized by a matrix, by an element. And it's actually half of that. This is the true domain, not what I saw in my computation. So you'll be off by the size of the stabilizer.
Just like this theorem you're writing down is a theorem, again, assuming that you have this trivial stabilizer.
So at the moment it's a definition, and the theorem will be, and maybe I've given it away, theorem, okay, I can define this set regard whether this condition is true or not, and the theorem will be if the stabilizer of Z0 in gamma is trivial, then this Dirichlet domain centered at Z0 is a fundamental domain. Does that make sense? And so if you want the actual fundamental domain, instead of taking I, you can take 2I. Okay, so here's I. If I take 2I, now I really will get the classical fundamental domain that's supposed to be a 2 as the Dirichlet domain. What if I take I plus a half? So here's I plus a half. That's right. I'll put the one that we expect to be here.
But are we assuming?
What are all the points that are closer to I plus a half than all of its images?
There's also stuff on the.
Yes.
Next to it, right?
Yes. So this half and that half go in, but nothing else. Does that make sense? So anyway, there's lots and lots of, the point is there's countably many fundamental domains for the action of uncountably many fundamental domains for the action of SL2Z. The classical one is just that. It's no more special than any other. Unless you have a reflection group. That's all. Okay, let me not go into reflection groups.
I don't know if you also asking about decomposition.
Yeah. Well, so this is an algorithm, right? I take my base point and I take the orbit of that base point under the group. And I get all these points, right? I'm taking the orbit of I plus a half. And then I look at all the bisectors between my fixed base point and its orbit. And every time I have a bisector, I cut out that curve. And I cut out this curve, and I cut out that curve, and I cut out that curve, and I cut out that curve. Yeah. All in the hyperbolic sense, which I have to explain what that is, what the bisectors are. And then most of the bisectors will be unnecessary, will be extraneous. I've already cut out this largest region, and then what's left over is the Dirichlet domain, which is a fundamental. Okay. All right. Let's get to what's distance. Okay, so we need a notion of distance. So how to get a notion of distance, how to do geometry on the upper half plane. Well, this is exactly what Riemann figured out, right? People were talking about people had until Riemann were really thinking of surfaces, and in those surfaces you're trying to figure out how do you measure, distance along the surface. And Riemann said, no, the right notion is that of a manifold, even if it's a surface. But what you want, so if you have a manifold, this is a crash course in Riemannian geometry. So Riemannian geometry. What is Riemannian geometry? Surface is just a two-dimensional.
Just like a function.
So yeah, the only difference between a surface, people were really thinking of surfaces embedded in R3, right? They're like a piece of paper that's wobbly.
Because in the manifolds have these charts.
Surfaces also have charts. So what Riemann said is the way to understand a manifold. So I'm drawing a two-dimensional picture, but now let's imagine an n-dimensional manifold. And in fact, it doesn't have to be embedded in any. It's just an abstract manifold. That's an even later understanding.
It doesn't have to be R3.
That's right. It's not in anything. It's just an abstract set that satisfies some conditions. The conditions are that around each point, so anytime I have a point Z in my manifold, anytime I have a point Z, there exists an open ball in the manifold, it's a topological manifold, and a map and a chart, and a local chart that sends this thing, so some map phi that sends my points to some Rn. And that's what I mean by an n manifold, is that it maps it to an open ball around Rn that takes this point to the origin. And if I have a nearby point, which also has an open ball, so now I have two maps to Rn, phi1 and phi2 is another map to Rn.
Differentiable map.
Exactly. If you want, depending on if you want topological manifolds or differential manifolds or smooth manifolds, you can. So now you have a map from Rn to Rn by precomposing on the intersection. You precompose phi2 inverse with phi1. You compose phi2 inverse with phi1. Now you have a map from Rn to Rn, and whatever class, so phi2 inverse composed with phi1, whatever class of manifolds, category of manifolds you want to work in, topological manifolds, twice differential manifolds, smooth manifolds, whatever it is, you just impose on the charts, on these transition functions.
But in practice, it seems nasty to be showing that you take these things, precompose, and then show that you have a differential.
It allows you to work abstractly in manifolds that aren't embedded in some Rm, where M is something bigger than Rm. In fact, it was a long-standing problem until John Nash solved it, of whether a manifold defined in this way can be embedded into some Rm, an abstract manifold. So that's the Nash embedding theorem. So Nash embedding theorem says says if you want to think about it classically, you can.
This has been coded up in some.
The manifolds are in Lean, and I think it's Heather Macbeth who showed that a sphere is a manifold. Gave charts, transition functions, and yeah. So this is in Lean. I'm just writing that. Oh, I don't know. I mean, that's a hard theorem. You need a lot of differential
This seems like a real sledgehammer within.
Yes, it was a major innovation.
I thought it mentioned anything about dimensions. The dimension.
Well, it also tells you, yeah, right, the question was, so, yeah, he definitely gives the best, or at the time, the best known bounds for that, yeah. Okay, so, where am I going? So, so far we're not doing geometry yet, because we could be in the category of topological manifolds. Where do we get geometry? Geometry is being able to measure lengths. Yeah, just continuous maps. Yeah. Topological manifold. I don't care about anything other than continuous. So where do we get geometry? So we need to look at the tangent space. So if I have a point Z in my manifold, I can look at the tangent space to my manifold. I guess I'll just call it TZM. So the tangent space to a manifold is you look at curves. So I want to look at curves, the set of curves, functions from, let's say, -1, 1 to the manifold, such that gamma of 0 is my point Z. And, well, especially if I want to actually do geometry, I want to, so I can take that curve. I'm going to abuse notation and draw that curve in the chart around, in some chart around my point Z. So this is my curve gamma. And if I insist that here, we're in Rn, so I can speak of derivatives. And I want to know that the derivative exists at 0. Derivative exists. So I want differentiable curves that have a meaningful derivative at 0. That's right.
And so mean derivative very much in the time sense.
Yeah, the classical, yep. I'm changing, x goes to, I like to call this t, time. T goes to t plus h. So in other words, the limit, I mean, I don't have to write this up. The limit of, as h goes to 0, this thing exists. Now that's too big because there's lots of curves that'll have the same derivative. So I want to mod out by the equivalence relation that two curves, gamma 1 is equivalent to gamma 2, if and only if their derivative at 0 agrees. Okay, so that's the tangent space to a manifold. Let's see what this means for hyperbolic space. I'm trying to define a distance in H.
Well, yeah, but I guess the question is why.
Oh, just for your general knowledge. Yeah, we could go straight to the definition. I could tell you what the definition is, but for the mathematical culture of where these things are generally coming from. Yeah, you'll see it's very so. What's H? Okay, so here's H. What's my chart? I have some point Z in H. What's a chart? We're going to get to Maass forms very soon. I promise. Today will be Maass forms. I better move a little faster, but yes. So what's my chart here? I guess I said it has to go to 0. So what's my chart? What's my map from the upper half plane from some ball around Z in the upper half plane? I just subtract Z. I just subtract Z and I get to the origin. Right. So the charts are trivial, basically. If you don't insist that this is the origin, well, I wrote that it's Z in the manifold, but it's the origin in the here. So right. So now we can think about curves. So what's the tangent space to at a point? What is TZ for the upper half plane? Well, what are the possible derivatives? The derivatives can be characterized by complex numbers. So this is all complex numbers, right? I'm just thinking of curves. They can go as quickly as they want through the point Z in any direction.
Yes, you're saying,
So I can identify the tangent space at a point with the complex numbers.
so you have this curve and then you might as well choose. You have a choice, right? Because you're taking equivalence here, and so you can just choose a complex number.
Yeah, I can choose a complex number in any direction of any magnitude. And then I'll draw a curve that has that. In fact, I'll draw the straight line that has that property. And then I pull that straight line by translation back here, and that's my tangent space. Okay, in the sense of Riemannian geometry, with this one, what this is trying to mimic is really the tangent plane to the curve. I'm thinking of a curve passing through in the manifold through this point, and what are the directions?
Right, like you could choose.
Just one derivative. All I want is one derivative. Yep. Yep. Or in a neighborhood. Yeah. Okay, so fine. That's the tangent space. Now, here's where Riemann comes in. So Riemann says, in order to do geometry, what you need is a quadratic form on TZ. If I know what the, and a quadratic form that measures lengths. In other words, I want to assign to every IE to each curve, to each direction in the tangent bundle at Z, I want to know, I want Q of eta, which is some real number that tells me the length. I want this to be the length of eta. So let's think about this. Let's go back to R2. So R2, the charts are in the same way, translation. Okay, what's the quadratic form? So I have an eta in the tangent space to Z in R2. Eta is, so here's some point Z in R2. Eta is typically denoted dx dy. So its x component is dx, its y component is dy. What is the quadratic form? How am I going to measure distance in the unit tangent bundle? Dx squared plus dy squared. Okay, so this is the Euclidean quadratic form. It's just the standard sum of two squares quadratic form. Euclidean quadratic form.
It's like what happens. I don't know, this still feels like kind of weird. Right, like why did people try to like work with the upper half plane and these Mobius transformations and stuff with like the regular metric? The realization that the upper half plane, so the upper half plane as a model for hyperbolic space comes much later than the development of Riemannian geometry. But like how did people connect these things in a sense, right? Like these Mobius transformations and the stuff we've talked about, you've required no geometry whatsoever, and yet they fit over H.
The method is preserved for the group. That's the point. So the Euclidean method is not preserved for the SL2. But the recurrent method is preserved for the SL2. That's why it's the group.
Okay, now the answer.
Yes. Then that's next thing we're about to do. Once I define, so on the upper half plane, what quadratic form will I take? I'll take the same two derivatives in x and two derivatives in y, divided by y squared. What is y? It's the y, so you get a different quadratic form. What Riemann says is at each point, you have a different quadratic form that measures the lengths. And so this is the quadratic form at z. The y is the y of z. It has nothing to do with dy, which is the dy of eta. Okay, does that make sense? So if I have a point here at 3 plus 4i, and I have a normal vector in its tangent bundle that's 2 plus 5i, what is its length? So the length of this eta, well, the length squared, right? The quadratic form is the square of the length. The length of this eta is 4 plus 25 over 4. The y is the y of the base point. We have a different quadratic form. I mean, maybe it's better if I write this as imaginary part
Right.
of z,
Not the same point, but what's the point?
right? It's not it has nothing to do with the denominator is not correspond to eta, it corresponds to z,
The dx and the dy correspond to.
eta, right? Does that make sense?
Then like this differential thing you've written down, it's just relevant when you're integrating things, or
Well,
that's
so
written down on this like, kind of arbitrary notation.
yeah, because I use dx.
Right,
Sure.
right.
If you want to use whatever you want to use for eta, I mean, this is just the classical. When you see these things written, this is what they mean. You should know what they mean. But actually, they will be. We're going to integrate them right now, because once you have a way of measuring distances, once you have a way of measuring distances locally at every point, you have a way of measuring distances in general.
I guess my question was about like why this is represented with this notation.
Yeah, it's because we're going to define the length. So given a curve, let's stick to the upper half plane where I think, so to try to speed up the presentation, given a curve gamma, let's say from 0 to 1 to the upper half plane, so here's gamma, starts over here, ends over here. This is gamma of 0, this is gamma of 1. How do we determine what the length of gamma is if it's differentiable? I'll integrate from 0 to 1, and at every point t, I'll measure the arc length. So it's the integral of what? It's gamma prime of t. That's a complex number. The absolute value of that is the length of this vector. But that's not the length of that vector in the tangent space at z. I have to divide by the imaginary part of gamma of t. And I integrate that dt.
Sorry.
Yes. What is length? How do I measure the length of something? I take little bits of arc length and I add those up. So at each point, I have a way of measuring the distance. That's exactly what this Riemannian geometry metric gives us.
That's not, and that's like,
And that's the square of the length.
right, so that Q is sort of in there.
This is Q.
That whole.
This whole thing is Q.
And the
Q is-
absolute value you're writing down are like
The absolute value, this is a complex number. I mean, this is
the.
as a complex number, right? The derivative, I'm saying the limit exists. These are complex numbers. So some ratio of complex numbers has a limit. I get a complex number. The absolute value of that is the square root of the imaginary part plus the real part. Square root of the real part plus the square root of the imaginary. Square root. That's the absolute value. The denominator is the imaginary part of z. The quadratic form has all these things squared, and the square root of that is the length. So this is the length as measured at each point by a different length. And this is what it means for a curve, a differentiable curve, to have a length. Does that make sense? Lewis is with me, but I think Carol is against me. No. It makes sense what this is? Let's do it. Let's test it. Oh, okay. Oh, okay. So the frustration is that you want me to move faster, not slow. Got it. Got it. So let's see. What are the geodesics? What are the geodesics in H? Geodesics are minimizing. So geodesic means you have a point Z, you have a point Z and a point W, curves of minimal distance, minimal length between Z and W. Okay, so what's the fastest way to get from Z to W? Well, if Z and W are, if one is right above the other, there's no reason for them to be on. So if this is Z and this is W. Okay, let's imagine a curve that goes from Z to W. So gamma of 0 is equal to Z, gamma of 1 is equal to W. Okay. Yeah, and so I want to minimize, we want to minimize the integral from 0 to 1 of, let's say gamma of t is x of t plus I y of t. Okay, just parametrizing gamma. So what's the derivative? Well, this is again x dot squared plus y dot squared square rooted divided by y of t, integral dt. Right, same thing.
I mean, you're minimizing this, over arbitrary.
Over curves, over all differentiable curves from z to w.
How many of you are there?
Uncountably many. But the question is, how do we minimize this? Well, I claim that one thing you could do is you can make the derivative in x 0. The quadratic form is y squared, and the length is the square root of the quadratic form.
How?
So this is y in the denominator. Okay, so this is always at least the same thing if I drop a positive part in the numerator, which is y dot squared, well, square rooted squared, so absolute value of y over y. Right, if I drop this term. So actually the best thing to do is to just go vertically. So minimal curve is vertical. The other thing is that this absolute value is, well, if the derivative is always positive, say, then this is minimized when I don't turn around, when the curve doesn't change direction, doesn't change the sign of y prime. Right, that you don't want to go up a little bit, back down, and then keep going up to the curve. Okay, so so the upshot of this is that one geodesic, if z and w have the same imaginary part of z is equal to the imaginary part of w. You can
go up and then you go down.
Why? You can do it smoothly.
All right.
Yeah. If the geodesic is straight vertical line. Straight vertical line. Does that make sense? Okay, so far so good. And then what happens in general? Well, now I want to use, now I want to understand how SL2R acts to come all the way back to your question. How does SL2R act on the tangent space? Well, the tangent bundle. So the tangent bundle is just the collection of all of these tangent spaces together. You can think of this as the disjoint union of all of these tangent spaces together. So if I have a point z and a tangent vector zeta, so here's z and a tangent vector eta, and I have an element here g. So g sends z to zz, gz. What does it do to eta? How can we figure out what it does to eta? So if I take z and I change it by a little bit in the direction of eta, and then I apply g, where does that end up sending g eta?
And that's what you're saying should be the new data.
Exactly. So g should act on z and eta together and give me gz. G is going to go where it goes. And then where is eta supposed to go? So if you compute what the differential is, so if you differentiate az plus b over cz plus d, so what is this? I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared.
The derivative, you're saying, okay, this derivative should not be that derivative.
Right. So the ACZs cancel, and I get AD minus BC. So I get 1 over CZ plus D. Not absolute value squared, but just squared. So in fact, that's what should happen to eta. Eta gets multiplied by this, and it's divided by CZ plus D, quantity squared. And I claim that this is this action fixes lengths. So this action of SL2R doesn't change lengths. Just the chain rule.
Right.
So if you think about a little change if you think about eta representing a little translation in that direction, then it's the same translation, but just how G is acting on both of these and moving things a little bit. If you think about it for a minute, I'm trying to, I promised I would get to Maass form, so I'm trying to get there. The action of SL2R is isometric. So it doesn't change the distances. So not only does it not change distances, the reason it doesn't change any distances globally is because it doesn't change any distances locally. Let's look at the length of eta over CZ plus D. So this is my new curve. My new curve is bless you, eta over CZ plus D squared. I want to know what the length of that curve is, but it's being measured at GZ. It's not being measured at Z. Right? You understand what this means? The length of eta at Z is eta as a complex number divided by the imaginary part of Z. I'm trying to show that when I moved Z to GZ and eta to eta over CZ plus D squared, I haven't changed the length of this.
So you need to show that is equal to.
Yes, I want to know that this is equal to this. Okay. So, well, what is this? Again, the way I'm going to measure lengths at GZ is to divide by the imaginary part of GZ and just take the length as a complex number. So this is eta over CZ plus D squared. Let me remark again, this is not an absolute value. This is a complex number. CZ plus D is a complex number. Eta is a complex number. And so this quotient is some complex number. But when I take the length here, the absolute value, I will get the absolute value, not just the square. So this gives me eta over absolute value of CZ plus D. I'll still write it as squared, and then there's my absolute value. Now, what happens to the imaginary part of GZ? The imaginary part of GZ, we did this calculation, yes.
I'm sure we have.
I think we did it last time. Didn't we do it last time? The imaginary part of GZ, okay, let me put this formula here. I thought we did it, maybe not. Over absolute value of CZ plus D squared. Did we not do this? Yeah, I thought we did, okay. So if that's what the imaginary part of GZ is, I'll put that in and I get absolute value of CZ plus D squared. And of course, these things cancel.
So there's a new metric.
With this metric, exactly, unlike if we use the real metric, just the Euclidean metric, it would not be an isometry. With this new metric, it is an isometry. You divide by Z, by imaginary part of Z, then whether you're measuring things at Z or at GZ, they'll have the same length.
I guess the idea is, yeah, because this is something that wasn't like super clear to me for a long time. So the idea is if you want to do topology on the upper half for
Geometry, yeah.
then it's like, since your important objects are like these things you're acting by and all these things, it only makes sense if your geometry depends.
Yes.
And this is the way you need to have.
Yes. Okay, and with this metric, we get a constant -1 curvature Riemannian metric. Let me. I do want to get to. I need one more thing to get to Maass forms, which will also finish the discussion, the definition of a modular form.
What is the modular?
Because curvature is one very major. This is what Gauss observed. You know this the Gauss pizza slice theorem, that you can't without ripping, you can't deform. So you can take a pizza slice and you can fold it, and that doesn't rip anything. But once you fold it one way, if you take your pizza slice and you fold it like this, to eat it, if it's too hot, then it will deform. But if it's not too hot, it's not going to fall flat, because in order for it to fall flat, it has to develop a hyperbolic, a place where it's hyperbolic, where its geometry is hyperbolic, whereas it started out being a flat slice. So here the curvature is everywhere 0. Curvature is like the difference between when you walk around a disk of small radius around a point. It should take you, if this length is a, it should take you 2 pi a. The distance around should be 2 pi a.
Because you're saying on this side, the pizza is gonna have to rip.
It's going to have to, if it's going to fall down, it's going to fall down because it's too hot and it's hasn't formed yet. But if you fold it this way, then you can hold it like this and the corner won't fall down. So you can eat it. You know this is, you take a pizza, you fold it in half.
Yeah.
This part doesn't fall down.
Yeah.
Why doesn't it fall down? Why isn't gravity pulling it down? It's because it would create a point of negative curvature.
Well, it's like explaining when you make a map of the sphere.
That's another way of, yeah.
I guess my question was sort of a bit more, why do we care that like the upper half plane or our number theory sort of,
Oh.
why do we care that we have -1 constant? Because it's just like.
At the moment, yeah, fun fact. At the moment, it's a fun fact, but it's
Does this ever come into play?
it's a fun fact, but so much of I think we definitely discussed last time how if we start with I and we move by a distance x, or we move by a height y, and then we move by a distance x to this point x plus iy, or we then multiply by that scaling matrix, we get over here to x to y yxi plus yx plus iy. Yx plus iy by that scaling, that this length and this length are actually the same under this Riemannian metric. That's a manifestation of the constant negative curvature.
But if the
So-
curvature were different, you'd still be able to say, then if the curvature went 1, then we'd still be able to say something like this, right?
Yes.
So it's
Yes,
not
this-
particular to like curvature -1.
It just so happens that with this, so let me move past this,
Yeah, yeah.
but there's a classification of complete Riemannian curvatures, manifolds with complete Riemannian curvature, and it's either 0, positive, or negative. And if it's positive or negative, you may as well make those +1 or -1 by just rescaling.
We can talk about it.
Yeah. Okay.
Sorry for dragging this down.
No, it's okay. Where are we? We're almost there. So we just showed how SL2R acts on the tangent bundle. And in fact, that allows us to define the unit tangent bundle. So the unit tangent bundle is T1 of H, which is the set of all pairs zeta, eta in the tangent bundle, with the property that the length of eta measured at z is 1. So I don't want just any directions. So here's my point z. I don't want to take all directions, all possible directions. I want to take unit length directions in any direction.
This is gonna help them getting this isomorphic.
That's right. That's right. So then there's a fact is that we can identify. So this is another space on which SL2R acts. And because it acts by isometries, we can in fact identify SL2R, or now I really do have to put the PSL2R can be identified with the unit tangent bundle of H. So whereas the subgroup SO2 stabilized I, if you recall, SO2 acting on I does nothing, fixes I, but SO2 does do something to the tangent vector at I. So if I'm at I have my tangent vectors, and this element SO2 will get me all the different, will move me around to the different tangent vectors.
Location won't change, but
Right. So the base point is fixed, but these are all moving around. And now you have again, you can get from any points to any other point you can get from I up, I comma I, if you want to think about this, can be mapped to any Z eta by an element of SL2R by now choosing the appropriate element on SO2
make sure the direction matters.
to make sure the direction. Okay, and so we're almost done. What is the who are the geodesics? So if Z is right on top of W, then it's the vertical line. If Z is not on top of W, so if Z and W now are in general position, if Z and W are in H, a theorem of Apollonius is that there exists a circle through Z and W and orthogonal to the real line. So there's a circle that does this. And it's constructible by straight edge and compass. And if you take these 2 points, so let me call these 2 points alpha plus and alpha minus, and I apply a map, there's a map that will send alpha minus to 0 and alpha plus to infinity, and Z can be somewhere along this direction. I could put Z at I. W will go somewhere. And now I know what the geodesic is. The geodesic is the straight line. And so when I pull that back, this will be the geodesic. So in other words, what this is doing is pulling the knowledge of what the geodesics are in vertical directions to the fact that this circle is indeed a geodesic in here.
You'd have to argue this with these integrals, but then using, right, that the action is respecting this.
That's right.
How you
Yeah, so there exists an element G in SL2R. I'll let you guys leave this as an exercise. There exists an element of SL2R which sends alpha minus to 0, alpha plus to infinity, and Z, well, Z is going to be on the curve between those two. It will send Z to I. And in fact, that's once I specify that Z goes to I, it's unique. All right, so those are all so now we know the geodesics, who the geodesics are. The geodesics are either vertical lines or semicircles orthogonal to the boundary. Okay. We're almost up to the point where I can define the measure, invariant measure. So what is an invariant measure? Invariant measure on H and the unit tangent bundle of H. In other words, I want to be able to integrate a function over some domain. And if I write here d mu of Z, that should be invariant under replacing F with G of Z and replacing, well, let's say the domain is the entire upper half plane. So in other words, I want to measure so that d mu of G is equal to d mu. I want d mu of GZ to be d mu of Z. What's an invariant measure? We've talked about invariant measures because we did them for the p-adics. So what's an invariant measure? So I have my point Z, which is x plus Iy, and I claim that the measure dz, d mu of Z is equal to dx dy over y squared. I claim that this is invariant. Invariant under the action of SL2Z.
And what that means for the integral is that, right, when you apply the
SL2.
Jacobian and
Yes.
figure all this out, that you can actually legitimately change the right, so act by this and it doesn't change.
Right. So one way to see that is that any element, so G has this so-called Iwasawa decomposition. Iwasawa is a fancy name for a very simple thing.
You already talked about it.
Did we? I don't remember.
I mean, it's basically what you did to
right, that there's a unipotent. So this is a unipotent. We talked about unipotents. We talked about diagonals, root y, 1 over root y. And we talked about SO2, cosine theta, sine theta, negative sine theta, cosine theta, but I don't know that I put them all together. So every element G can be uniquely written as a matrix decomposition like this. SL2R, yeah, SL2R. Although this is something in general, right? This is just like the QR, I forget which one's which. I want to multiply by an orthogonal matrix and make things upper triangular. Is that QR? LDU. Anyway, I don't remember. It's been a while since I taught linear algebra and remembered all those acronyms. Yeah. Which acronym is which? But anyway, any matrix can be made upper triangular. In this case, it's trivial. If I have a matrix ABCD and I'm trying to make it upper triangular, this is upper triangular, and I want to multiply by something on the circle to make it upper triangular, that's easy. I can multiply it by D negative C, and that will give me CD, CD, and minus CD. So that's going to get me a 0 over there. But so for this to look like this, I need a D here and a C there. But of course, the determinant of this is D squared plus C squared. So that's not 1. So I have to divide by the square root of D squared plus C squared. And if I do that everywhere, now this is a matrix of that form. And now whatever I get something, I'm going to call this A bar 1 over A bar. It has to be 1 over because the original determinant was 1. I'm multiplying by something with determinant 1. And now when I multiply by the right diagonal matrix, in fact, that diagonal is the right diagonal matrix will be the inverse of this, and then I can pick out what this element is.
And that is factor.
And I just factor G as unipotent times a diagonal times a compact. Okay, does that make sense? So far, so good. Okay, so because we have this decomposition, it's enough to check that each of these kinds of elements individually preserve this this form. And in fact, it's enough to check that at I by the homogeneity. So at I, this element doesn't even do anything. So it, of course, preserves the form. At I, so translation by something is dx is invariant under translation, horizontal translation in x, which is what this matrix does. So the only thing we have to check is what happens to this thing. Okay, so I send Z to yeah. So if I have some diagonal matrix, alpha 1 over alpha, or square root of alpha, times Z. This is alpha times Z. Alpha is a real number. What happens to dx? What happens to x? X goes to, well, it gets multiplied by alpha. What about y? Y gets multiplied by alpha. So dx dy over y squared becomes dx is alpha times dx. Dy is alpha times dy, and I get 2 alphas in the bottom. Okay, so this is invariant.
Why does it suffice on the generators?
Well, because any matrix will be a common, because it's an action. So I can, if it's invariant under the first thing and the second thing and the third thing, then it's invariant under the whole matrix.
Change it once, then change it again.
Yep. And the last thing, as long as we're here, let me tell you what an invariant measure on the unit tangent bundle is. So the unit tangent bundle again is z's and etas, where the length of eta is 1. Well, if the length of eta is 1, then you can think of eta as an angle, theta. And in fact, under the identification of this with SL2R itself, we can give a measure on SL2R. So dg, we can write as dn dA dk. So this is an n, a, k decomposition. dg will be dn dA dk, where dn is dx, dA is dy over y squared. So that's our same dx dy over y squared, and dk is just d theta in the in this variable. And I'll let you check that that what this does to the tangent vector is, right, it's c. I'll let you check that this is invariant. It's easy to check.
You're translating this. You're giving both.
I'm giving both at the same time. Yeah. So there's an invariant measure.
For T1H, and this one is.
That's right. This is in the T1H coordinates, and SL2R itself has a harm measure, and this is the harm measure on SL2R. Because SL2R can act on itself. This is an invariant harm measure on SL2R.
I'm viewing SL2R as some subset of R1.
If you like. Yeah, you can do that. Okay, so we're almost there. Because now what we have is L2. This is what I wanted to get to. I said everything needs to be L2, but in order to have L2, I need a measure with which to measure things in L2. So we have L2 of the upper half plane mod SL2Z.
I'm sorry.
Please.
So if you transition from SL2R to DSL2R, you have to divide by this.
I'll have to divide by negative. Well, you mean here?
Yes. No.
I haven't normalized these things. Yeah. So Haar measure is unique up to normalization. Yeah. So I'm looking at this domain, this subset of the upper half plane, and what is the invariant measure? Well, we have an invariant measure now. So the measure with which I want to measure things is our d mu z. So this is, what does this mean? This is functions from the upper half plane. This is functions or equivalence classes of functions from the upper half plane to the complex numbers, which are invariant under SL2Z. F of gamma z is equal to f of z. And square integral. So the integral of absolute value of f of z squared over this domain D. I can choose any fundamental domain for this where to integrate, because the measure is invariant, dx dy over y squared. Infinitely many choices for D. But along any of those choices, this integral will be the same.
Right, when I said you can't do like H instead of D.
No, I definitely can't do H here instead of D. That's right.
D is what it says.
That's right. Okay. And there's one more thing, and then I can actually define a Maass form. And then I'll tell you what a modular form is. So far, so good. There's a Laplace operator, and then we're going to move. This is all background information that we're not going to use. This is all to motivate what we're going to do when we start working at Dirichlet. I want to know this whole story. It's okay that we don't have this whole story perfectly in place. We're going to see it again several times, and we do it periodically for each P, and then we're going to put it all together and do it at Dirichlet. So that's why I'm okay with rushing this part of the presentation. There's a Laplace operator, this invariant differential operator. The hyperbolic Laplace operator in x, y coordinates is the Euclidean Laplace operator, two derivatives in x, two derivatives in y. That would be the Euclidean Laplacian, and a y squared. So this is the thing that exactly counteracts the fact that we have a Euclidean metric divided by y squared. So this is the Laplace operator. This is the Laplacian. Where it comes from, yes. So there's a general formula for the Laplacian in terms of any Riemannian, what the Riemannian structure is. And there's a calculation.
I have a question, but not to answer.
Please.
Like I saw in another class that Laplace depends on the weight of the form, like there is an additional term.
That's right.
So like I'm not real. I thought that one Riemannian means one Laplace operator.
Yes.
So why there is multiple?
Because here we're talking about invariant functions. Modular forms are not invariant. They have a factor here. So that's a weight. And so now you can look at functions that are not automorphic, but are modular, that have a weight, and that has a different Laplace operator, because so it's not a function on D anymore. It's not a function just defined on D. It's a function that has a different structure. And there's a way to make a function that's invariant out of a function that's modular. And the Laplace operator on the automorphic version is the weight K Laplace operator on the original. I'll try to say that right now, actually. Again, but first let me tell you what modular form is. So a Maass form is a function that is in L2 of, let's say, H mod SL2Z. Of course, you can do, we can look at much more general quotients. That is an eigenfunction of the Laplacian. That's it. So a lot of, as I was saying, the definitions you'll see in a book are, it's an eigenfunction of the Laplacian, it's invariant under gamma, and it grows at most polynomially, because it's so we only need to give its definition on this domain. The only non-compact part is that it's, we have a compact X region, we have a compact X and Y region, and then we have this sort of region that at infinity. And it's in that direction that we need to know that it grows at most polynomially. Why? So that it can be integrated. Because once you know it grows at most polynomially, actually you know that it decays exponentially and hence is in L2. But the right way to say it for me is that it's in L2.
Think you really need polynomial? That sounds like over.
It is overkill. You could say it's bounded. Well, so as I said, this is the definition that I consider the proper definition. And so this implies, I will tell you, but not today, why. This implies that actually, if it's a Maass form, then phi decays exponentially. Decays exponentially. Well, if it's a Cuss form, it decays exponentially. It's bounded. It's bounded. Is bounded.
So in other words, if you have an eigenfunction of this Laplace operator, this is actually going to be a stronger condition.
If you might have an eigenfunction of the Laplace operator that's invariant under gamma, but is not L2.
So it being L2 is such a strong condition that in fact will imply this
Right.
boundedness and
Yes,
whereas ordinarily the need to be fixed.
that's right. That's right.
I just don't see the weight. I mean,
We haven't done anything with width. Okay, so now let's look at a modular form, and we're out of time, but let me just say it immediately. For a modular form, we have a function. I don't know why I switched from ph's to f's, but let's just go with it. A, B, C, D of z is not just f of z, but it's cz plus d, cz plus d to the k. And so if you look at something like f times imaginary part of z to the k over 2, this is almost invariant. The absolute value of this is an automorphic function. Is automorphic. Exactly. So the difference between so there's something called the Petersson inner product. 2 S's? Anybody? Petersson inner product, also inner product, is if you have a modular form of weight k, 2 modular forms of weight k, f and g, you don't want to just integrate over the upper half plane mod SL2z of f of z times g bar of z times dx dy over y squared, this invariant measure, because this function is not invariant under SL2z. I can't form this quotient. So Petersson says, oh yeah, just stick in imaginary part of z to the k, where k over 2 of them go to f, k over 2 of them go to g. They come with complex conjugates. So this thing is invariant. This thing is automorphic. And hence can be thought of as an L2 space. So that's a weight k L2 space. And there are Maass forms of weight k, which you can get to by raising and lowering operators within the bigger thing. And the bigger thing, okay, so this is the last thing I'm going to say. The bigger thing is not to decompose upper half plane mod SL2z, but to decompose SL2R mod SL2z with respect to dg and the action of g on functions here. And this decomposition will contain all modular forms and all Maass forms and at all weights in terms of irreducible representations. Okay.
Wait, so here you're saying like modular form,
Yes.
you start with a modular form and you're making a Maass form out of it?
No, what I'm no, this will not be an eigenfunction of the Laplacian.
Hmm.
Modular forms are eigenfunctions of Cauchy-Riemann equations. So that's the difference. Instead of there are no weight k modular forms.
I guess what was the point of
Non-zero.
talking about modular? Why do you start talking about modular?
Okay, because what's really going to happen is we're going to take L2 of g, but not all of g, just the gamma invariant functions of g. G is SL2R. We have a Haar measure on g. We have an invariant measure, and we have an action, right regular representation, just as before, acts on functions. And you want to decompose this space into irreducibles.
Okay, in the same way that we were.
In the same way we were doing. When you do that, you get several things. Some of them will correspond to, I have to explain how this is going to happen. But the big picture is that modular forms will contribute irreducible representations and Maass forms will contribute irreducible representations.
And that's why they're thought of as related.
They are related. They're the different kinds of, so modular forms will induce a discrete series representations. Maass forms will give us principal series representations.
And then do we just translate everything to the matrix setting because linear algebra is nicer?
Yes,
It seems to be a theme.
this is good fun. Yes.
Sort of embedded into matrix groups and then.
Yep.
What is it?
Okay, I got to Maass forms in a rushed way, but we'll go much more slowly, and this is our target. But at what cost?